Okay, just ping me, yeah.
Yeah, if I see you go to question, I'll try to alert you.
Thank you. All right, good evening, everyone, or at least good evening to those in South Africa. Seems to be some feedback. Tonight we have a wide-ranging session covering AI-enhanced search and discovery, topics on reproducibility, and new approaches for software tools and development teams. Kicking us off will be Rachel Street with the Tom Toolkit. Please take it away, Rachel.
Hello, everybody, and thanks very much for giving me this opportunity to present. Our team's work focuses on using software to meet the challenges associated with coordinating astronomical observing programs, and I'd like to tell you about some of the tools that we've developed for this purpose. But before I go on, I want to give all credit to our development team, which is a collaborative effort between the software development team at Las Cumbres Observatory and our in-house scientists. Let me start by quickly recapping the scientific motivation for our software tools. As you know, modern astrophysics has entered an era where we have a wealth of targets of all kinds. A wide range of surveys are in operation at all wavelengths and messengers, generating vast catalogues of discoveries and data products in the petabyte range. Advances in data processing mean that many surveys also issue alerts of new discoveries in real time, and the rate of alerts is expected to increase by an order of magnitude over the next few years. Improvements in survey technologies have, of course, opened up new areas of parameter space, and astrophysics has discovered new phenomena such as kilinovae and confirmed the existence of phenomena that were theoretically predicted but technologically hard to detect, such as gravitational waves. Massive object catalogues, including extensive time series data, are enabling us to understand the evolution of different categories of objects by studying their population distributions. This wealth of discoveries means that researchers from all branches of astrophysics are facing the same challenges of searching this huge haystack of data for the needle of the targets that they are particularly interested in, and collating all relevant data on those targets from a wide range of sources. If the targets are static or relatively slow to change, this can be a very labor-intensive task. But for those targets which change or move rapidly, the challenges are compounded by the need to act quickly to ensure that all necessary data is acquired while the target can still be observed. Furthermore, for many areas of science, the survey discovery data alone isn't enough, and additional follow-up observations are needed in order to characterize each target. This was highlighted in 2016 by Nagita et al. They conducted a study of the follow-up instrumentation that will be necessary to characterize a range of different targets detected by the Vera Rubin Observatory's Legacy Survey of Space and Time. As you can see from this table, almost all branches of astrophysics will require additional data from multiple different facilities in order to complete their science goals. Now, other speakers have done a great job of describing the data archive and alert broker facilities that are designed to provide astronomers access to the survey discovery data. But once those have done their job, what's the next step to achieving our science goals from those data products? Even though any one astronomer or team may be interested in a specific subset of survey discoveries, they still have a lot to keep track of. There's a constant stream of alerts and new discoveries to be evaluated, often within hours if your science happens to focus on transient phenomena. Some of those targets will need further observation, and those targets must be identified, prioritized, and an appropriate observing strategy decided on. This means that researchers have to constantly juggle lots of different targets, all in different phases of evolution, some newly discovered and some the subject of long-term study. Quite often, teams have to manage observations involving a number of different telescopes and instruments in order to characterize a single target. And although the resulting data products are smaller than those for a survey, there is still more to keep track of than is feasible for even a team of human beings. Just the follow-up program alone can involve thousands of observations and terabytes of data. And not least, you need to coordinate the human team behind your project. And these days they are often geographically distributed. Everybody needs easy access to the project's data. Software tools can be an extremely powerful way to help teams to manage these challenges in a sustainable way and to enable them to achieve their scientific goals without being overwhelmed. Database-driven systems designed to manage astronomical projects and their associated data can act as a bridge, interfacing with data archives and other astronomical services to enable researchers to more easily accomplish their science. As a general category of software, I'll refer to these as Target and Observation Managers, or TOM systems, and a number of research teams have independently developed such systems for a wide range of different science, from the FRITZ system developed by ZTF and the Supernova Exchange, to the NEO Exchange system for studies of near-Earth asteroids. Although a number of such systems have been developed by various major projects, they are not trivial to build from scratch and require substantial software development and database expertise that is not universally available to the whole community. Nevertheless, when you look closely at some of the systems in use, it's striking how many common features they share, despite having been designed for quite different science goals. This indicated to us that it would be valuable to build an open source package designed to make it easy for any astronomer to build a TOM system and customize it for their science, without having to reinvent the wheel or become an expert in database design. The TOM Toolkit package is designed for this purpose. Our approach is to have the core package developed and supported by LCO's professional software engineers, working in close collaboration with astronomers both at LCO and in the wider community. We aim to provide a base toolkit that supports the commonly used functions and interfaces to avoid users having to reinvent the wheel, but we also designed it so that even a novice developer would be able to customize it to their own workflow. The package is written in Python and based around the Django web framework so that the system can be accessed simply from a browser without the users needing to install some local application. At the heart of a TOM system is a database which is designed to store data on astronomical targets. The TOM includes a browser-based user interface, and the base toolkit includes many of the displays and user interface tools that are commonly needed by astronomical projects. Naturally, this includes the interfaces needed for astronomy, but it also includes the underlying project infrastructure, such as managing user accounts. The package includes a fully featured TOM system out of the box with a setup script that talks you through the setup process. So it's quick and easy to have your own TOM system up and running within minutes. The database is organized around the user's set of targets of interest and all associated data. While the default database is set up for basic parameters such as name, coordinates, etc., this parameter set is designed to be extended by the user to include information that is specific to the science in question, such as modeling parameters, for example. The TOM also supports the constructions of lists of targets and includes essential search functionality and interactive plotting tools which assist the user's workflow. But the design of these pages is highly customizable. As you can see here in this example of a target page that has been customized for supernovae follow-up with the SNEX-2 system built by Jamie Burke, Craig Pellegrino, and Andy Howell. It's particularly important for the toolkit to provide interfaces to a wide range of external services in astronomy, as this allows the user to quickly and easily collate data and alerts on their targets of interest, evaluate the combined information, and make decisions about their scientific strategy for each target. Thanks to the powerful programmatic interfaces provided by many alert brokers and data archives, it's increasingly possible for researchers to automatically receive notifications of new discoveries of interest and to gather the information they need via software. This also speeds up the workflow, meaning that researchers can respond more effectively to new discoveries, particularly transient phenomena that require a rapid response. Rather than have every research team reinvent the wheel and produce many versions of effectively the same interface software, the toolkit provides a set of built-in modules to handle these interactions with a range of public alert broker facilities. We also provide interfaces to a number of data archives, and we are keen to partner with a wide range of other archives to expand this list of supported facilities. The toolkit provides the means for users to upload their own data products to their TOM as well. These can be raw or processed data associated with observation requests, or standalone data products, such as those produced by user-developed analysis software. The toolkit includes tools for uploading data in many common formats, including time series data, and the JSON-based ingest is very flexible. Users are encouraged to adapt it to upload data in whatever format is most suitable for their science. The toolkit also provides built-in tools for data visualization to allow users to inspect their data directly within their browser. These are very interactive and include image display tools as well as interactive plots, which can also be customized. One of the most powerful capabilities that a TOM offers is the ability to submit requests for additional observations directly to telescope facilities. This streamlines the follow-up of all kinds of astronomical targets and significantly reduces the workload of managing observing programs, especially when multiple telescopes are needed. A range of telescope facilities now offer such a service, and the number is increasing all the time. For this reason, the toolkit includes a set of built-in modules and interfaces that allows users to submit observing requests, monitor their execution, and harvest the resulting data products from telescope archives. Once again, we are keen to partner with a range of observing facilities to make more instruments available this way. In addition to the browser-based user interface that comes with the toolkit, I want to emphasize that most of its functionality can also be accessed programmatically. All modules include APIs that are designed to allow the functions to be called directly from external user-developed software. There are a range of scientific motivations to do this. For example, choosing which targets are of interest to a user's scientific research and prioritizing those targets is obviously something that is highly science-specific and has to be user-developed. In many cases, selection algorithms can be written, which has the advantage of very clearly quantifiable selection biases. The toolkit provides APIs to enable this software to interface directly with the TOM. Likewise, data reduction pipelines can also interface directly with the TOM, for example, to streamline the upload of reduced data products as soon as they're available. This is a crucial element in enabling fully robotic project management, which not only reduces the workload on researchers, but also makes the project more efficient and able to react more quickly, which is particularly important for transient science. The toolkit has a number of features that offer project teams flexibility in how they run their program. The first is access control permissions. By default, any TOM user can access anything in the TOM, but we recognize that not all projects can work that way. Users can then indicate which groups should have access to which targets by selecting appropriate checkboxes, as you can see from this section of the Target Create view. Similar access controls can also be applied to records of observations and to data products at the discretion of the administrator. Another feature that the TOM offers is support for predefined cadence strategies. It's often the case that astronomers can define their observing strategy in advance, even if they don't know exactly what their targets will be. For instance, when a supernova is detected, an observing team who have applied for time on a given telescope know that they're going to be taking time series imaging in multiple filters every few days, and likewise spectra. This may need to continue for several months. So a common situation is that a team nominates a suitable target and requests a set of observations, but weather or another factor might conspire to interrupt the time series. With perhaps hundreds of targets to monitor at any given time, keeping track of these observations can become quite a high workload on the human team. So the toolkit supports observing strategies which enable the TOM to carry out predefined observations for you. Users can write a small Python function which tells the TOM what to do under certain circumstances. The toolkit includes an example that will automatically resume an expired observing request in the event that no observations were obtained within the given time frame. Our team has consciously sought to partner with a number of other service providers in astronomy from the outset of the project, and we're delighted that a number of partners have contributed plugin modules that enable users to interact with a range of alert brokers and telescope facilities. So a big thank you to all our partners. We would very much welcome the opportunity to work with additional astronomical services and support a wider range of functionality, so please get in touch if you're interested. We also provide a range of extension modules for the toolkit. In most cases, these include functionality which we feel is widely beneficial, but which sometimes makes use of external packages, which causes a little bit of extra complexity when a TOM is deployed to a public server. To ensure that the base toolkit is kept as simple as possible to use, these packages are optional. The extension modules cover a wide range of additional features, from more interactive plotting tools to an interface for a developing platform for multi-messenger alerts. But there is one module that I would particularly like to highlight. Multi-messenger alerts present some distinct follow-up challenges, as the initial discovery data is often not well localized. And the first task for research teams is to pinpoint the specific source of the signal, and to do so very quickly before the event becomes undetectable. By definition, they must collate information from a number of different sources in a meaningful way and streamline the evaluation process as much as possible. And it's often the case that they will have a number of candidate targets associated with the same event. Our team have been collaborating with Andy Howell to develop this new user interface. It's designed to help follow-up astronomers collaborate to create prioritized lists of candidate targets, coordinate observing requests to a variety of facilities, receive the resulting data, and then reevaluate and eliminate non-viable candidates. At all stages, it keeps collaborators informed of all findings and activities until the source of the event has been determined. We are working to have this available as soon as possible, and certainly by the O4 gravitational wave detector run. These new, more responsive JavaScript tools have been built using the Vue JavaScript framework. This has allowed our team to implement a number of reactive user interface elements, such as candidate tables that can be sorted or searched on with a single click. The framework is integrated with the toolkit in such a way that it will be possible to extend the number of reactive tools we have available, so that all users will be able to take advantage of the smoother workflow that they offer. We also hope to extend the TOM Super Events module in future to support coordination between teams of observers. When a high priority event is discovered, it is often the case that many teams will attempt to follow it, and services such as the Treasure Map system are designed to make this process more efficient by helping observers to coordinate their efforts. More and more observing facilities are developing programmatically accessible interfaces, and this has been a particular priority for the Rubin Observatory, to increase our capability to efficiently respond to alert streams. So expanding the number of facilities that the toolkit supports is naturally an ongoing priority for us. This is highly complementary to another software project by the Las Cumbres teams, the Observatory Control System. For any telescope operator, the control system for the facility is obviously critical, but time-consuming and expensive to develop in-house. This is something that at Las Cumbres had to do when we developed our network. So we are now repackaging our control software into a standalone software package that can be used independently by other facilities. A key aspect of this system is that all core functions can be performed by API, meaning that they can be easily incorporated into web interfaces and software to support different workflows. And this includes integrating the facility with the TOM toolkit if desired. The package includes a browser-based observation portal where users can submit observation requests and monitor their progress. This module stores the observation schedule and provides APIs for a telescope site to access that schedule and update the status of each observation. The APIs mean that the observing programs can operate robotically, enabling more reactive science. The scheduler generates an observing schedule for the telescope based on the request submitted, and feeds this information back to the portal. This system is based on LCO's own algorithm, which is highly adaptive, meaning that it generates a new schedule whenever there are changes to the requested observations or the state of the telescope. The scheduler supports several modes of observations, including normal requests that take place within a user-specified window, and time-critical requests that receive higher priority to ensure that they take place at a specified time, such as for a planetary transit, for example. The system also supports rapid response requests that need to be executed as soon as possible. Provided the target is visible from the telescope, these requests will begin within 15 minutes. The package includes a data archive system designed to store data products from the observatory and make them available to users via a browser-based interface, which also offers API functions. This provides fast and reliable access to the data, which is again well suited for reactive science. Every observatory must obtain routine calibration data for all of its active instruments, and Las Cumbres is no different. Since this is in reality a specialized type of observing program, when it came time to overhaul that element of our software, we chose to use the TOM toolkit to manage calibrations across the network and to provide our operations team with suitable monitoring tools. This is a screenshot of Calibration TOM's display of spectroscopic standard star observations in progress for our different telescope facilities. Our TELOPS team are able to start, stop, and pause observations for specific standards, but otherwise the TOM will continue to manage these automatically. We are currently working to include photometric calibrations as well. I'd like to wrap up by highlighting the user support that our team offers for anyone developing a TOM system. The package has extensive online documentation, and we also provide a set of training materials that work through installing and customizing your own system. We also run a developers forum as a virtual meeting and a Slack channel where research teams can directly contact our software engineers to ask for advice on TOM development. So thank you for your attention. And if you have any questions, I will be happy to answer them.
Thank you very much, Rachel. I see there's a question coming through. Perhaps while we wait, I can ask one of my own. Very impressive. So one of the, broadening this to radio interferometry and millimeter interferometry, scheduling an interferometer has additional complexities in UV coverage, and there's an opportunity for optimization there when considering multiple requests. Would you envision this incorporating something like that, or would you leave that up to the observatory or the users with that Python script you mentioned?
That's a really great question. And yes, scheduling multiple facilities has been something that the team has talked about for some time, but it involves a lot of various complexities if you are talking about facilities that are not under central control. So the advantage with the scheduler that I just showed you is that it's designed to work with all facilities that are under a single institution's control. So for an interferometer, although it hasn't been applied in that context, one could imagine that it could be adapted for that purpose, because an interferometer, those facilities are all under an individual institution's control. The real complexity happens when you start trying to schedule observations when you involve multiple observatories, all of which have their own user bases and all of which have their own policies. And that is an outstanding challenge that we have not yet investigated.
Thank you. Okay, so we have a few questions here online. The first is from William O'Malley. The observatory control mentioned looks a little bit more like an observation scheduling system. Does it contain instrument and telescope control modules?
So it incorporates all of the different elements that one needs to operate an observatory, but obviously every observatory has its own instrumentation. So that is handled as a configuration, which the user is able to set in advance and would obviously tailor to their own instrumentation.
Great. Next up, Stephen Gwynn. How do you set priorities between fields? And a second question, is my asteroid more important than your supernova?
The age-old question. The TOM system itself and the scheduler don't set any priorities. That's important to know. So the priority of one observing program relative to another on any given facility is up to the time allocation committee that awards time on that facility. So we assume in advance that a facility has allocated time according to whatever protocol it follows, and the TAC has awarded some kind of priority ranking to the different proposals that are in operation. And that proposal priority is part of the configuration that when the TOM system submits observation requests to that facility knows in advance what the priority of a given proposal actually is relative to everything else that it's doing. So it's on the telescope operator has complete control over what programs it prioritizes relative to another.
And then David Buckley asks, I suppose he was in the room earlier, but is no longer, if I'm correct. Would you like to comment on the synergy between TOMS and Aeon? Can the latter work independently of TOMS?
Right. So TOMS becoming compatible with the TOM toolkit is one of the two avenues optional that a facility can take if it wishes to become compatible with the Aeon multi-facility network. But there are other options. So if a facility has, for example, its own API systems and its own control systems existing already, then it's entirely welcome to use those. All it really needs to do to be Aeon compatible is provide APIs that can be programmatically addressed and run at least part of its schedule in a queue scheduled operation. And that makes it very, very flexible for time domain observations. But compatibility with the TOM toolkit is one of those options.
Great. Ryan Timmons asks, does the OCS have any support for space-based telescopes or instruments?
Oh, that's interesting. So the Open Control System was primarily aimed at ground-based facilities. But one thing that is becoming more and more available now is there are APIs being developed for space mission facilities. In particular, the Swift telescope springs to mind. And we are in the process of speccing a module for the toolkit that we would like to be able to submit observation requests directly to Swift to make advantage of that API. So that's definitely in the future development category.
Great, thank you. Any last questions for Rachel? I don't see any typing, so let's have a round of applause for Rachel, please.
Thank you all.
Thank you very much indeed. So next up we have Michelle Ntampaka talking about building trustworthy machine learning models for astronomy. Please take it away.
Hi folks, my name is Michelle Namaka. I am delighted to be here today. I have pre-recorded this talk, and at the moment I am in the Discord server to chat and answer questions. So I am delighted to field those questions as you're listening to the recording. So today I want to talk to you about building trustworthy machine learning models for astronomy. And I'm going to start with a claim that I think would be bold at any other conference, but perhaps not so much at this one. And that is, I believe that astronomy is the ideal sandbox for machine learning. Why do I think that? We enjoy minimal privacy concerns. Unlike healthcare records or purchasing histories, we're not terribly worried about privacy issues with our data. Astronomy has a culture of sharing data. We have well-posed questions. We enjoy public interest and support. Our data are non-monetizable. They can't be used to sell things. And I do want to clarify that I don't believe that this exempts us from ethical concerns, but it certainly gives us sort of a wider and freer sandbox in which to work. Now, astronomy may be the ideal sandbox for machine learning, but one thing that we as a field need to wrestle with is machine learning the right tool for astronomy? We need to ask ourselves the big questions. Can machine learning be trusted? Can it be trusted with our valuable data? Can machine learning be used to make new physical discoveries? And what role will machine learning play in the future of astronomy? And I think these are going to be common themes throughout this conference as we explore these ideas of ML for astronomy. I'm going to focus in on that first one for this talk. I have 4 suggestions for ways to build trustworthy machine learning. First, build trustworthy machine learning models with interpretation. What do I mean by that? Okay, now for everybody who's on the Discord right now, what I'd like you to do for me is I'd like you to answer this question. How can you tell that this is a horse? I'm actually going to pause here in the video so that you can go answer that question in the chat. How do you know that it's a horse? Okay, I'll make some guesses. At this point in time, give yourself a point if you are the person who suggested the mane or the tail, or that it has 4 legs. You get 2 points if you have suggested the color is what's so horsey about it. All right, 3 points for anyone who has suggested the shape of the face. I'm going to give 10 points to whoever said it's horsiness or who claimed something about just the essence of horse. All right, and 100 points goes to the final category. Anyone who said it's in a green pasture with a white fence in the background. All right, how can machine learning tell that it's a horse? We might have a similar discussion about these items. There's a really interesting paper that explored exactly this question. In their image classification algorithm, they looked at the why. Why can this tell it is what it is? And they found something really surprising. In their horse images, the most informative pixels were the ones that made up the copyright stamp of the horse photographer who stamped all of their horse photos in the bottom left-hand corner. So here is an image taken from that paper. In the top left, a horse with the copyright stamp and a heat map showing in bright red the importance of those pixels. Remove the copyright stamp in the bottom left-hand corner, and this is no longer classified as a horse. Even more concerning, you take that copyright stamp and you add it to a picture of a car. That car is suddenly classified as a horse. There are stories of this all over the literature. For this particular one, I did not pull an image from the paper, but rather from a sales pitch. Winkler et al. 2019 found in an analysis of skin moles, a convolutional neural network that was identifying whether the mole was dangerous or not dangerous. They found that the most important thing in that classification was markings made by a dermatologist with a skin marker that they would often put in there to identify worrisome moles. So what we want to do here as astronomers, we want to make sure that we're building, that we're testing our models, that we're building interpretation into it as a way of building trustworthiness. Okay, the second thing we can do to build trustworthiness is to use concise language. I'm going to call out one thing in particular, and that is overfitting. Overfitting is broadly misunderstood among the astronomy community. I would define overfitting as the model has learned the training data too well. This particular type of model will underperform on the test data. It will give pessimistic results. Unfortunately, much of the astronomical community misunderstands this particular word. Instead, what they're trying to say is something like overspecialized. In a case of overspecialization, the model has learned subtleties of the simulation, of the training data that are not true of reality, and that gives optimistic results. So if we want to build broad astronomical community trust in machine learning, we need to be careful and concise with our words. The third way that we can build trust is by scrutinizing especially tremendously good results. I'm going to show an example from my own research. The details of this are not important. What you need to know is that I'm showing on the x-axis of each panel the true value of sigma 8 in this case. On the y-axis, the predicted value. On the left-hand side are trustworthy results, which have a scatter at about the theoretical limit for the data set I gave it. On the right-hand side are suspicious results. In this case, on the right-hand side, when I ran my model and plotted it up, the very first thing I did was check to see if I was actually plotting error bars, because in fact, they have disappeared behind the points. I'm seeing here a factor of 10 better results than should be theoretically possible. And I need now, as a researcher, to explore this. This is not the time to publish. This is the time to approach with scrutiny. I need to be asking, is this trustworthy? And will it generalize to real data? In my particular case, in the suspicious results, my machine learning cheated. Those results are not robust. The model will not generalize. It turns out that it had picked up on a simulation artifact that was not true of reality. It had memorized that simulation artifact, and it had used it to reverse engineer the truth. All right, so we need to approach our really good results with scrutiny. And the final way that we can build trust as a field in machine learning is exploration. Right. Start with sort of the penultimate picture, I think, of exploration. So what I've got here is a photo of Buzz Aldrin on the moon. And Google has this really interesting tool called Deep Dream. It is gradient descent in the pixel space. It basically asks the question, how would I need to change this picture to change the answer? So in the case of Buzz Aldrin, right now, classified as an astronaut, but we could change the pixels to change the answer, and we get this terrifying result. You can see the dog from the hoses on Buzz Aldrin's chest. You can see the street scene kind of along the back. You can see a wheel well for a vehicle in the top right-hand corner and some pedestrians. In the middle to bottom left, you'll see a two-headed, many-footed bird. All right, changing the pixels to change the answer. What kind of use is this in astronomy? For any kind of deep learning convolutional neural network that is classifying or regressing astronomical images, this can be a very useful tool because it can point you to the regions that are most informative for particular answers. So hand it a picture, ask it to twiddle with those answers slightly to change the regression value or change the classification. I've used this tool in my own research to confirm some previous results about what part of a galaxy cluster contains the most cosmological information. Another way that we can explore is through showing our model data that it has not seen before, maybe sitting outside of the training set. This is a tool that I really like, Pixel Recursive Super Resolution. When trained on face priors, and I will emphasize that, it knows that it is looking at a face. It can take that left-hand column and reproduce the results in the middle, and the values on the right are the truth. All right, but tools like this can be highly dependent on the data set that you give it. And if you give it biased data, you can expect biased results. So here we see on the left-hand side an obvious image of Barack Obama, and on the right-hand side a pretty horrifying actually result of what happens when you have a bias in your data. I show this as an example to call out exploration as a way of building trust, to call out building data sets that are representative. But I also put this one in there to call out something I said at the beginning, which is, as astronomers, even though we have so much freedom to work with machine learning, that doesn't exempt us from ethical concerns. And we need to think carefully about how our algorithms could be used or misused. So returning to the original question, is machine learning the right tool for astronomy? And in particular, can it be trusted? Today, I talked about machine learning that it can be the right tool for astronomy if we do some things. We should interpret, we should explore, we should approach high accuracy results, too good to be true results, with scrutiny, and we should use concise language. Thank you so much.
Thank you very much, Michelle, for a fascinating talk. It certainly stretched me as a chair trying to do the parallel processing on the Discord barrage that you set off in asking whether that was a horse or not, why that was a horse. I won't repeat everything that's been said on Discord, but questions, please, from the room. And there are some philosophical questions, I believe, in the Discord thread that's just passed, but I see Peter Tubin is asking one. Let's give him a second.
That was a particularly fun talk to listen to and give, because I've never both been the teacher and the person chattering in the back of the room at the same time. So I got to hold both of those roles today.
I wasn't quite prepared for this at 20 to 9 in the evening after a long day, but anyway. Peter Tubin remarks, this ML talk has become very psychedelic. I would agree. Well, I'll go back to just before that barrage. You did say that our ML questions our questions in astronomy are very well posed. Is that true in the ML context? Do you think that that's in all cases where they're all well posed?
Oh, I like this question. I mean, no. Are all questions well posed? No. I think just one of the advantages that I wanted to call out here is that we have such a nice sandbox for machine learning researchers. Our data set can be very attractive because we have questions that we can ask concisely. Please give me the morphology of this galaxy. Please give me the mass of this galaxy cluster. Please tell me more about the spectrum of this object. As opposed to things like computer vision, which have more nebulous questions or a little bit harder to assess sort of the goodness of the answers to those questions. I think that was the particular thing that I was trying to call out in that point.
Oh, cool. Thank you. Many people are typing. I don't know if any of these are questions or more psychedelic images of horses or...
It really could go either way, couldn't it?
Very, very cool, though. Oh, great, Michelle. Okay, we have a minute or so before the next talk, but...
Every time.
Please go ahead.
It just makes me feel short. Hey, Michelle, it's great to see you. So what I think about when I think about building trust in machine learning is, of course, the generalizability of it. So we see loads of papers of people being like, look, I've got this great CNN and it applies to this data set and it does this great job. So I wonder if you can comment a little bit about building machine learning tools and approaches that are very general, that we can use for different data sets, that then helps us build as much trust in them as we have in things like Bayesian statistics and other tools that we use all the time.
Yeah, I love this question. Okay, I think I have two comments to that. The first is, I think it's very natural as a field that we go through this first step of learning, which is, I have a tool and it does really well. And the thing I really want to challenge you with, you actually just hit the nail on the head, is now let's go the next step further and try to explain the why, try to address that. As far as tools that have broad applications, I'm a little more nervous to speak strongly here. I know there have been some great advances in transfer learning. So train a model on one thing, apply it to something different. But I'm not certain that some of the deep learning techniques, convolutional neural networks, and others are advanced enough yet to really generalize. You typically see, even in the machine learning world, you've got a neural network that's trained to play Go or to play chess, not to play board games. And I think technologically, we're probably just still a few steps away from that sort of broad generalizability.
Awesome. Thank you.
Yeah.
Cool. Thank you, Michelle, for a great talk and
Absolutely.
lots of food for thought.
Thank you.
Right, next up we have Sankalp Gilder, going to be speaking about uncertainty-aware learning for improvements in imaging quality with CFHT. Please take it away, the floor is yours.
Hey, thank you. Let me quickly share my screen here. Okay. Is the screen visible and am I audible clearly?
Yes and yes.
Perfect, thank you. All right, the topic that I will be speaking on first is improving IQ at CFHT using machine learning. This has been done in collaboration with a large international collaboration consisting of 19 members in total, spread across the US, Hawaii specifically, Canada, and France. Our first paper, which was an extended abstract, was published at NeurIPS. Our second paper, which is the main paper, was accepted. This should actually read accepted at MNRAS, and we are working on a third ML paper that's in progress. A quick overview of CFHT. It's our first light in 1980. It's a 3.5 meter aperture telescope. And since it's on Mauna Kea, the native seeing is 0.43 arc seconds, which is, excellent. Very quick slide about what seeing is, though I don't think this particular audience needs, an introduction to it. The leftmost figure is good seeing, the rightmost figure is bad seeing. One great advantage of good seeing is we usually, astronomers, give telescope operators an SNR target for observations. The better you're seeing, the less time it requires you to reach that target SNR. And given how oversubscribed modern observatories are, any savings here can be significant. In this particular paper, we used data from MegaCam, which is the most productive imager at CFHT. The specific thing that we controlled using machine learning, or we proposed to control using machine learning, are the 12 vents that were installed in 2013 to reduce dome seeing. A quick graphic about what that is. This is the top view on the left side. On the right side is the front view. All modern observatories, ground-based observatories, including CFHT, have these vents cut into domes. The idea is that as air gets heated inside the telescope, these vents allow them to allow this hot air to go out and let the cool mountain air in. And as we know, cool air is good. It means less seeing, less turbulence. There are 12 vents around CFHT, as shown in the left figure. The current status quo, since these vents were installed, they've either been kept all open or all closed because they didn't really have a robust model which can control as a function of time which vents to open and which to close and how to do that. When the vents were all open, the best median IQ that was achieved on site was 0.48 arc seconds. And I remind you that the best native seeing, which means seeing if the same telescope was just placed out in the open air without a structure around it, was 0.43 arc seconds. So we are a little away from the native seeing. Using Kolmogorov's 5/3 law, if you subtract 0.48 from 0.43, you get 0.15 arc seconds. So this is the seeing that we aim to capture using our model. For both of these tasks, capturing the seeing and doing this via controlling the opening and closing of different vents as a function of environmental variables and a function of the observations themselves, we used ML models, specifically deep learning models. Like I mentioned, the reduction is possible to 0.43 arc seconds. A quick overview of the data. We have data from July 2014 to Feb 2020, a total of 63,000 samples. It's a regression problem with one continuous output, which is the scene, which we're going to call MPIQ or megaprime IQ. 119 inputs, out of which 107 are continuous and 12 are categorical. These are the 12 vents, which for this problem we have said can either be open or closed. In reality, they can take values intermediate between open and closed. However, this was sort of a proof of concept paper, so we went with either completely open or completely closed. I mentioned that when the vents were all open, the median seeing was 0.48 arc seconds, so that is what the histogram on the left said. For all the data, all 63,000 samples, we divided them into two separate categories. When the vents were all open and when the vents were all closed, and we plotted the histogram of the seeing. As you can see, vents closed gives you 5 arc seconds, and vents open gives you 0.48 median arc seconds. This makes sense because this is the whole point. The vents were installed to reduce the median seeing. Nonetheless, 0.48 is greater than 0.43, and that's the value that we want to capture. On the right is a sort of bar plot showing percentage of times all vents were open, all vents were closed, one vent was open, two vents were open, etc. Hamming distance from all open, the way to read it is on the x-axis, 0 means 0 vents closed, 1 means 1 vent closed, and 12 means all 12 vents closed. As you can see, majority of the times, 80% of the times, all vents were closed. This was either due to mechanical issues with the observatory itself or due to high winds on the telescope, on the mountaintop. The operators felt it was unsafe to keep the vents open, so they just closed all of them. A minority of the times, all vents were open, or at most one of them were closed. Our goal in this paper was to take this subset of samples and sort of toggle the 12 vents. Since each can take two values, so you create 2 raised to 12, which is 4096 hypothetical samples. Well, 4096 minus 1, which was the original base sample. And the idea is to figure out if these hypothetical samples, if any one of those for a given test sample is able to give you a lower seeing than you had gotten when the vents were all open. Just a quick overview of what the data looks like. I mentioned we had 119 features and we divided them into different categories. You have environmental variables. We have a ton of temperature sensors placed in and around the telescope dome. I mentioned we also use variables about the observation itself. So for a given observation, which means a given sample, what was the pointing, azimuth, altitude, windscreen position, the central wavelength of the filter, etc. And other variables we use are exposure time and the time of observation, what time of the night it was. I won't be able to go into a lot of detail regarding the exact implementation of the models, but suffice it to say we use two separate types of models. One is the mixture density network, which is a supervised learning algorithm, which maps the known inputs to known outputs. And unsupervised learning, here we use something known as a robust variational autoencoder. Here there are no outputs. You try to reconstruct the inputs. So it's essentially like this. It's a funnel placed on top of a reverse funnel, and you try to reconstruct the inputs themselves. Just to quickly describe why we use these two separate models, I mentioned we create 4096 hypothetical samples. However, if you recall from the bar chart that I showed, majority of the training samples have either all 12 vents open or all 12 vents closed, which means a bunch of these hypothetical samples with configurations somewhere in the middle, like 5 vents open and 7 vents closed, will be, to use the Emil lingo, out of distribution. Our goal is to identify what these out of distribution samples are and not make any predictions on them, since we will not be very confident of those predictions. An RVAE is a generative model which have been shown to be very good at identifying in distribution versus out of distribution samples. So what we do is we run our samples through an RVAE and we remove the hypothetical samples that are out of distribution. And for the in distribution samples, we make predictions using the MDN and we see if the predicted MPIQ is lower than the original MPIQ. And we note what the configuration was for those predictions. This is a quick overview of the mixture density network, what that looks like. As I mentioned, MDN is supervised learning. Here, something we do is instead of making point predictions, since our goal is to eventually push this model into prediction, you also want an estimate of risk. We don't want to say the MPIQ for this hypothetical sample is 0.6 arc seconds. We want to say 0.6 arc seconds plus 0.1 minus 0.2 arc seconds. And that will allow the observatory technicians to determine whether or not making that change in configuration for the vents is desirable, does it make sense? So instead of making point predictions, we made predictions for the entire PDF. And we did something else, which is known as post hoc calibration. Here, the idea is that neural networks are very overconfident of their own abilities. So if you train a network on pictures of just cats and dogs, and you give it a picture of, I don't know, a llama, it'll probably give you an answer with a very high degree of confidence that it's a cat or a dog. What we would want ideally is for the model to say, I don't know. Alrighty, thank you. So that's what we try to do with post hoc calibration. These are some of the results, predicted versus a true MPIQ. On the left plot and the right plot is a histogram of the predicted median minus predicted true for both calibrated and uncalibrated. And we can see, looking at the bias value, using calibration was beneficial to us. Then we use the RBAE. We use something known as beta divergence with beta likelihoods to reconstruct the samples. And using this, we were able to remove out of distribution samples. So if on the left side, you see a training set, a test set with all vents open and test set with the vents toggled, everything to the left of this vertical line is out of distribution and everything to the right is in distribution. As you can see, our intuition was correct. Most of these hypothetical samples are out of distribution, then a minority are in distribution. We ran a stress test on the right side to sort of verify that our model was indeed separating IT from OD samples. So we took the training set, which were normalized between 0 and 1, all the values, and we added Gaussian noise with these two sigma values. And we can see that it was actually able to reject with a very high degree of confidence the out of distribution noisy samples as indeed out of distribution. This is an alternative plot. Instead of using just the total loss from the VAE or VAE, we use another metric known as a likelihood regret, and we showed that likelihood regret actually gives you better results. So that's what we ended up using for our model. And this is really, after all of this dense technical stuff, here are the money plots really. So here we plot, using the procedure I mentioned, we identify the in distribution samples, which give you better predictions than using all vents open. And we plot those, the difference in median IQ versus measured IQ. And we see a median improvement of 0.17 arc seconds. And these are the vents for configurations when all with the hypothetical best optimal vent configurations. You compared, essentially what we did was we took this particular set of samples where all vents were open, and we asked ourselves, okay, for these, is it possible that there are other configurations which will give you better IQ? And turns out if you take this one, a large majority of those are 50% are still open, but then you get a division between, say, just one vent closed and all vents closed. And here is a similar plot. Is as a function of IQ. It's a bar plot which shows you if you look at just one bar right here, let's say this one, it shows you that when all vents were open, so it's dark brown, you get no improvement, which makes sense. However, when you close all vents, your median IQ improvement is about 0.5 arc seconds. So the way to read this is when the true measured IQ was say 0.9 arc seconds, closing all vents would have given you a better IQ. That's what our model predicts. And these are attribution plots for us to understand or verify to ourselves essentially a high resolution feature importance plot, if people are more familiar with that, to satisfy ourselves that the variables, the features that the model places high importance on, were indeed the correct variables. We compared it with CADBoost. I don't think this is particularly relevant here. These plots basically show that using a neural network with regularization gives you better results than a boosted tree model, which are known to be poor extrapolators. So just to verify for ourselves, and CADBoost is also not able to predict any improvements. Okay, I think that's all I have for now. We're the first ML-based mentoring solution for ground-based observatories, and when we push it into production, it will be the first such model to be in production. Thank you.
Great, thank you very much, Sankalp. We're a touch over time, and we've got a couple of questions, so I think I'm going to defer those to the channel afterwards, I'm afraid. But thanks very much indeed. So next up, we have Emily Lakdawala talking about taking passengers on planetary exploration vessels, benefits of engaging space enthusiast communities with rapidly released image data. The floor is yours.
Hello, everyone. I lost half of the introduction while I was switching to the breakout room, but I think it's my turn to talk now. So I'm going to just get my screen sharing started. All right, so hi, and thanks for the invitation to speak to you at this conference. I'm honored to participate, and I hope you enjoy the presentation that I have for you. I'm here to advocate for the public. That's been my role for quite a long time now. Before I get started, though, I should mention that if I can get this slide to advance. There we go. Okay. All of the images that you'll see in this presentation are courtesy of NASA or NASA JPL, unless I note otherwise. And the images that are in this presentation that are not from any NASA or any other government agency that have been that are derived products may be copyrighted. So, like a lot of people, my interest in planetary exploration began in the 1980s with the flybys of the giant planets of our solar system by the Voyager missions. And I was captivated as a kid by the even these kind of very fuzzy images of the moons of Saturn and Jupiter and Uranus and Neptune. The ones of Uranus in particular had lovely names like Miranda, Ariel, Umbriel, Titania, and Oberon. These pictures are not the highest quality images we have of targets in deep space, but they were brand new worlds. And I think that the public tends to be really inspired every time we see a new world in space. Just imagine the excitement when we first encountered the rubber duck shape of Rosetta's comet, Churyumov-Gerasimenko. I'm very excited about the Lucy mission that just launched. That's going to be seeing a whole lot of strange potato-shaped new worlds once it finally encounters them in the Trojan clouds before, in advance and behind Jupiter. But at the time, I was just an impressionable kid, and I didn't really think that I could possibly have a career in space. I studied a lot of science. I went on to do geology, and I became a science teacher. And it was while I was a science teacher in 1996, 1997, that some very exciting things were happening in space. There was this landing on Mars of this lander, Mars Pathfinder, with this very charismatic little rover. And all of this was happening at the same time that the World Wide Web, this absolutely new creation, was just getting underway. And NASA began with Pathfinder a tradition of sharing images out to the World Wide Web. And so that they invited the public along to enjoy the drama, the adventure of exploring a new place, a new planet, via the venue of images shared across the internet. And it's something that's just expanded and grown more important ever since. At the same time, Galileo was also returning images of those moons of Jupiter that I had so enjoyed in the Voyager pictures when I was a kid. And having my geology degree and seeing these images, I suddenly had this epiphany: can you do geology in space? So it turns out you could. I went to Brown to study geology, and there I made a discovery that would change my life. It's not the kind of discovery that you publish in a journal. No, it's the discovery that there's a vast quantity of data, as you all know, that's been returned from numerous missions across the solar system, and that it's actually available to the public. This was a revelation to me. I spent my 2 years at Brown rifling through cabinets when looking at these wonderful images of Venus from Magellan when I should have been working on my thesis. And I realized that I'd found my calling, that what I really wanted to do was to share these images with the public, to let the public know that these images existed, and that there are so many more images of these other worlds of the solar system than are generally visible to the public, because they're in this, this treasure trove, this library of data that most people don't know about and don't know how to access. Well, fortunately, a year after graduating from Brown, I was able to get a job that allowed me to do this kind of proselytizing to the public about space image data. I joined the Planetary Society in 2001 in order to work on an education project associated with the Mars exploration rovers, and initiated by these two young men, Steve Squires and Jim Bell, who were involved in leading the Mars exploration rover mission. Steve Squires is a principal investigator. Jim Bell was the head of the camera instrument. And they had this idea of sharing all of the images from the rovers to the public as soon as they landed on Earth. This was very different from what has been done in the past and what's been done on most missions, to be honest. Most missions wait for a certain period of time, months to years, before sharing their data to the public through data archives. But Squires and Bell decided that they wanted the public to join this adventure, as Pathfinder had before, and that was Matt Gollenbeck was in charge of that one. And so on landing day, you can see here on your screen some of the very first images that were returned from Spirit, the same images that we saw in mission operations, the rest of the world could see at the same time. These somewhat funny looking images show the rover still on its landing deck, and actually the camera mast hasn't even opened up yet. So you're looking down the mast before the camera mast is raised up. And so a huge international community developed around these rapidly released images. There were just people around the world who were able to download these images and follow the adventure. You can see in this image that they followed that some of the amateurs noticed this dust devil before NASA or JPL had a chance to write a press release about, oh, we found dust devils on Mars. And so by sharing these raw images with the public, the mission was able to generate a lot of excitement, a lot of loyalty, a lot of interest and education about what it takes to explore space. The experiment was so successful that JPL repeated it with the Cassini spacecraft just 6 months later when it went to orbit at Saturn. And after the Mars Exploration Rover project, the education project that I was working on ended, I was tapped to start educating the public, as had been my hope, about how to use these images, how to process them, and how to make the most of them. Just another 6 months later, the Huygens probe landed on Titan, and their images were released to the internet somewhat inadvertently, but almost immediately after they arrived. And at the same time that the European Space Agency was releasing image panoramas that looked like this, there were members of the public who were producing images like this. This is a panoramic view of the landing site taken by Huygens and showing kind of the color of Titan sky and of the just strangely seaside looking landscape that Huygens saw as it descended. So when I discovered that amateur community, I discovered that amateur community when I was working as a journalist covering the Huygens landing. And I immediately needed to find out who these people were, what motivated them, how they can aid space exploration and education, and how I can help them, what barriers they face that prevent more people from participating in the very fun activity of processing space image data in order to produce beautiful photos. So after spending a lot of time within this community, I figured out that the major motivating question that a lot of people ask who want to do this kind of image processing is, what would it look like if I were there in space looking at this target with my own eyes? If instead of a robotic spaceship, it was actually a spaceship carrying humans, what would it look like outside the porthole window? And so this means that they have very different goals in mind when it comes to processing images than scientists do. So here's an example of a pair of images of Venus that were produced by two different missions, Magellan and Galileo, and they were both released by the missions in order to do some public science education. The Magellan one is a radar image. It shows you the surface of the planet as seen in radar data. And then the other image shows you the upper cloud decks of Venus. And it shows you, what Galileo could see through an ultraviolet filter. And so both of these images were released. They're some of the most commonly reproduced images of Venus that you can see across the internet. And neither of them actually looks like what it would look like if you were there. And so here's one of my favorite images produced by one of the amateur image processors, a guy named Matthias Malmer, Swedish guy. And this is a global view. It's a very high resolution view actually of Venus from Mariner 10. He has incorporated a little bit of ultraviolet data so that you see a little bit more in the way of cloud features than you would if you were there. But at the same time, it presents a much more realistic view, a much more natural color view of what Venus would look like than those previous images that I showed you from the science releases. If you want to know what Venus would really look like if you were there, you can use messenger data. This is a color image of Venus processed by a Croatian guy named Gordon Ugarkovic that shows you what Venus looks like. It looks like a cue ball. And so this is not an image that really edifies you very much scientifically, but it does answer that question of what would Venus look like while you were there. Here's another of my favorite examples, two of the most commonly reproduced images of Neptune and Uranus from Voyager 2. And you see this sharp color contrast with Neptune being dark blue and Uranus being vaguely aqua colored, when in fact, if you process the images to simulate what human perception would look like, this is the contrast between them. They're really very similar looking planets. Uranus at the time that Voyager 2 passed by had quite a lot less cloud features than Neptune did. It actually probably looks a lot more like Neptune now that the seasons have been turning over. And so here's a montage that I put together of all the planets and moons of the solar system using amateur processed images to represent them as close to natural color as they were capable of producing. And I feel like it makes a much more natural, a prettier illustration. Again, it may be less useful for science, but it has really high illustration value. So what do artists need if we're going to be helping them out? They need data. They need metadata that describes what is in the data. They need data and metadata in order to be able to browse and search. They need tools that help them zero in on the data that they're looking for to find the kinds of data that will allow them to produce these beautiful illustrations. They need batch download tools that make it easy to download large quantities of data that doesn't require them to know a scripting language, because a lot of these people, they're artists, they're not coders. And so they need help with these activities in order to be able to get at the data that they need. They need processing tools that they can understand how to use, or even better, already calibrated or reprojected products that are more accessible to them. Just in general, you need to, most of these artists, with a few exceptions, notable exceptions, don't have the technical expertise necessary to interact with these gargantuan archival data sets. They need things provided to them in easier to access ways in order to be able to do the kind of work that they're capable of doing. What do you get from these artists if you support them? The obvious answer being gorgeous illustrations for your work. A favorite example of mine for this is the Voyager 2 Miranda dataset, which is one of the gnarliest data sets from the Voyager 2 mission. Voyager 2 flew past a very small moon, Miranda, quite close by. It's a 500-kilometer moon, and it at the time was not able to take images in very rapid succession because in part of the low light levels at Uranus. So even though it got this really pretty set of images, there's a total of 8 images of Miranda for this mosaic, there's a lot of perspective change between them, and Miranda is a very lumpy moon. So if you go to the JPL website and you look for the officially released mosaics that were produced from this data set, these are the two options you get. The first one is a kind of poorly puzzle pieced version that's basically just made by sliding the images around and trying to match them up as best as you can. But because of the perspective changes, they don't match together very well. The other one is a reprojected version that has also had the photometric changes taken out. So it looks very flat. This is a version that was produced for mapping purposes in order that they could map all of those groovy features on Miranda. And it's definitely a much better mosaic than the other one, but it also doesn't look like a moon floating in space. And so here's a version of that data set that was produced by an amateur named Ted Strike. In order to do this, he had to do a lot of manual warping. He also replaced some data with some lower resolution data that was to cover one area on the limb that wasn't covered by the high resolution data set. This is far from a scientific product. It is not, it is slightly fictional because he has been, he kind of rubber sheet warped things in order to fit them together, not using mathematical reprojection. But it's a much prettier illustration, and it's a better, it forms a better impression in people's minds of what the moon Miranda would really look like if you were there. Here's another example of Ted Strike's work that I really like. So this one begins with some cleaned up versions of Russian Venera lander data showing the surface of Venus. You can see the top one has some platy lava flows, the bottom one has some blocky lava flows. And here are versions that Ted Strike created using those images as the kind of raw material for these artworks. If you go back and forth between them, you can see that the pictures of the surface of Venus that he created are based on reality, but they're not real places. These are not actual photographs. They are artistic products based on a true story, is kind of how I like to describe these images. But they help the public perceive, understand much better what these original, very warped, odd perspective images actually look like, what the surface of Venus may actually look like. And then my last example of this is something that I love producing these scale image montages. But one thing that always bothers me when I see them in presentations is that people often have everything like rotated every which direction with respect to each other. And it looks very false. It looks, it's disconcerting to have the illumination coming from multiple different directions. So I just scale everything and then rotate everything so that the sun is coming from the top, and then everything hangs together much more pleasingly. In this particular combination, I also tried my best to adjust the levels of each of the images to reflect their actual albedo. And so you can see the huge albedo contrast between things like comet nuclei, like at the bottom, you can see Halley, Borrelly, Tempel 1, Bilt 2, Hartley 2, and Churyumov-Gerasimenko, and the rest are visited asteroids. And you can see how much brighter most of the asteroids are than the visited comets. So in addition to getting excellent illustrations, you can also, by engaging with these artists, you can crowdsource your PR. You can get a lot more conversation about space missions happening across social media, and you know, it broadens your impact a great deal. So here are some examples of some really amazing amateur image data artists. There's Gordon Ugarkovich, who I've mentioned previously. Thomas Apperet mostly works on Mars. Judy Schmidt does a lot of really amazing work with telescopic data. Justin Cowart is a man after my own heart. He does everything. So this screen cap from his Flickr shows Rosetta images and Saturn and Mars. Some of these Mars images are from Viking. So it just goes to show the kinds of work that can still be done with very old data. And then when I was at the Planetary Society, I created a landing page where I collected some of the better examples of amateur processed images, and I did my best to connect them with metadata that described which mission, when, what filters, all that kind of information, so that you have a little bit more information available than you typically do when you see these things shared on social media across the internet. The only thing about working with amateurs is, of course, you have to remember that they're volunteers. And so even there are some missions like JunoCam has actually used volunteer help in order to process their raw images into beautiful processed works. JunoCam is not a science instrument. It was put on the Juno mission purely for EPO purposes. And so they don't have a team. They don't have a science team whose task it is to process the images. Instead, they rely on volunteers, members of the public, who then submit their products back to the NASA website. And they've produced some really glorious work with the JunoCam data. Some of them even have very scientific approaches. So John Rogers has been observing Jupiter for a long time with the telescope. And so he takes these images and identifies the belt and cloud features within them. Of course, not everything that the public submits is quality enough for hanging on your wall, but it's fun. People do enjoy a great deal having the opportunity to interact with missions in this way, and it really does engage the public. So I'm gung-ho for even the most psychedelic versions of the Juno image data. So the last few minutes of this talk, I'm going to talk about how to help amateurs access this data. Most amateurs prefer to use those kinds of data sets that are rapidly released to the internet. This is confusingly referred to as raw data, but it's not the same thing that most of us are thinking of when we think about raw data. For them, raw refers to the rapid release data. So these data are released by certain missions straight to the website. They're available nearly in real time after they've landed on Earth. Sometimes there's a short delay of a day or a few, but most of the time they're available really quickly. These data usually go through an automated pipeline that does not include calibration or flat fielding or other steps like that. They're also usually automatically contrast stretched and saved in some kind of lossy compression format, which makes them more accessible in terms of being able to see and understand the pictures and download them quickly, but it also reduces the data quality substantially. It would be nice if these artists were using the archival data, the much higher quality data, but they find it very difficult to discover and to use it. There are a few missions currently sharing this kind of raw image. These are kind of raw images, and I've got a list of them here. I can put more links to these websites in the Discord later on after my talk. And there's a large number of missions have done it in the past and have engaged with the public really effectively this way. There are a few missions and cameras that work very hard to release their archival quality data very quickly. So Mars Reconnaissance Orbiter HiRISE releases as fast as 1 month after data acquisition. The Rosetta NavCams got up to near real-time release toward the end of their mission, and Bepi-Colombo MCAMs are I think on only a 3-week delay. And then one thing that I think is very cool is that the director's discretionary time that's awarded on the Hubble Space Telescope, those data become available to the public almost immediately. There are some really excellent browse tools out there, and I've put links to these in the Discord for this talk. My favorite one is the Opus Rings Node search tool, which displays you your search results using colorized versions of all the images that show you what kind of intuitively what color filter they were taken through. So I can say, aha, this particular image set has a red, green, blue filter combination that I can use to combine into a color image of Saturn. And so it makes it much easier and more intuitive to search through the archival data. I served earlier this year on an independent review board that NASA convened to look at the whole planetary data ecosystem and say, what kind of work does NASA need to do to make its data more accessible, usable, machine operatable. I headed up the searching subcommittee, and we issued a report in April 2021 offering advice to NASA on how to do what kinds of actions to take in order to make the planetary data ecosystem more effective and more accessible. We found that there is a huge tension between the preservation of data and its discovery and usability. So that NASA's planetary data system is really excellent at preserving data, but their mandate wasn't originally to do any, to make it especially discoverable or usable, especially to communities who were not working on the mission itself. It was mostly about preserving, saving the data for use by future researchers. And so that has resulted in a situation where understanding how to discover and to use data really depends on your having access to other members of the science community and people working at data archives. And this is all fine and good if you are a graduate student with a mentor who can help you out, or if you're an employee at a NASA center. But if you're a member of the public, you don't usually have that kind of access. And so there are insurmountable barriers to understanding where to find, and how to use this kind of data. There are problems like there being too many portals, steep learning curves for using the data, and the fact that a lot of the data that's preserved is low-level data that requires calibration in order to be able to use it. There are some missions that archive calibrated versions of their data sets, and I love them very much because I don't have access to IDL or other tools that are commonly used by people in the community to do the calibration steps. And I don't code, so I can't write my own scripts to do that. So there are ways that this community can help increase public access to data by doing things like building browse tools, simply writing the instructions in more accessible ways on websites. That includes, simpler language makes it more accessible to people who don't have specialized education. It also makes those websites work better with machine translation to make them accessible to people in countries who do not speak English as their first language or as their scientific language. It's useful to make data available in more common lossless formats like PNG. And there are a couple of missions, notably InSight, which is now sharing its data in PNG format. And then it would be great if there could be easy to use, maybe browser-based tools for common processing tasks like making anaglyphs, color combinations, animations, that sort of thing. And so that's just a high-level overview of the kinds of work that amateurs do and the kinds of things that they need in order to help them do their work more effectively. And if we can increase access to all of these amazing images, then we can really get a lot more public education about our space missions and also invite a lot more people to participate in a way that I think will make them gung-ho supporters of future space exploration. So thank you very much, and I welcome questions.
Thank you very much, Emily, for a stimulating talk with some beautiful images. We have a few questions in Discord. The first is from Ketchel Kirkham. In the naturalistic image of the planets made by space enthusiasts, why is Jupiter's south pole not blue, as in the Juno NASA images?
That is because of perspective. It's because when you look at, my understanding is that when you look at Jupiter's poles from a shallow angle, you're looking through a lot more of the upper atmosphere. There's a lot more haze, and it kind of grays out the color of the poles. But if you have a more down perspective on them, then you're seeing more directly that blue color. So I think it's just a scattering effect. It's a limb, it's like a limb brightening effect, I think. But you'll have to ask a more expert person on Jupiter's atmosphere to see if my answer is correct on that one.
Thanks. There's also some discussion on the provenance of some of these images shared as JPEGs on public websites. Perhaps you can comment on that.
I'm not sure I understand the question.
So a question from Peter Tubin was, is good provenance always shown for some of the JPEGs that are shown on public websites in whether it's just a caption on the side, where this actually comes from, and differentiating from artistic versus scientific or science-ready images?
So if you're talking about images that are shared by the missions themselves, yes, they do share some metadata with it. They typically share things like time of acquisition, camera that was used. They may share range information, location information, that kind of thing. So there is some metadata that's shared. One of the things that is not commonly shared that I really wish is that nearly every image from every mission is taken with some kind of observation identification or a scientific justification. And so you might have images where it's like, part of an observation made for a global mapping of a world, for instance. And when the Cassini images were shared, you didn't get that information released with the JPEGs. Now, the Cassini mission did share observation plans for each of the targeted flybys. So you could put that together with images that were the JPEG images that were released, but that was an extra step that while I was interested in doing it, a lot of members of the public wouldn't have done that. And so that limits the usefulness of some of the images, but they did share enough usually to identify the target of the images and the time of day and things like that. So they do share some metadata.
Great, thank you. There are a suite of new questions coming in the Discord, but we've unfortunately run out of time. But let's all thank Emily again for a stimulating talk and some beautiful imagery.
Thanks very much.
Right, so next up we have Felix Grieses talking about building AstroBert, a language model for astronomy and astrophysics. The floor is yours, Felix.
Yes, hi everyone. I had to turn off this live feed from the main. Hi everyone, I'm gonna play a video and hopefully it sounds good. I should have, based on what I might test, it should work well. All right, can you confirm you can see the video? Great. NASA SAO Astrophysics Data System. And today I'll be... Okay. Sharing the computer sound.
We had it briefly, but it stopped.
Hello, everyone. My name is Felix Grez. I am the machine learning and natural language processing expert at ADS, and that is the NASA SAO Astrophysics Data System. And today I'll be presenting our work on AstroBert, and that is a language model for astronomy and astrophysics. So some brief background to understand where we're coming from. ADS is a NASA CFA project. It's been in service since 1993. It was actually announced at ADAS-2, and it is a digital library of astrophysics papers. And it provides many tools and services to explore its millions of records. Standard filters like author, year, title, which can be also allows for more sophisticated. Yep. My video is showing is the issue.
I think it's your Zoom controls that are in front of the screen. I don't know how to remedy that.
All right. You just can. And it is a digital library of astrophysics papers. And it provides many tools and services to explore its millions of records. Standard filters like author, year, title, which can be combined with Boolean operators such as and, or, not. But it also allows for more sophisticated queries such as exploring the citation reference graph, finding co-reads, or sorting papers by similarity. We are always looking for ways to improve ADS, and in recent years, there have been many advances in the field of information retrieval, natural language search, and we would like to take advantage of them, and we think we are in a unique position to do so because we have direct access to so much data. That's why we are building a language model for astrophysics, which we are calling AstroBert. So why build a language model? The example I like to give is, if you ask an astronomer for papers from the ESA Planck mission, they will be able to understand you mean the space satellite, not Max Planck the author, or Planck the institute, or the Planck constant, or any of the other meanings of Planck. The astronomer is able to navigate the inherent ambiguities of natural language from contextual clues. Context of the query, the context of the data, all that is information the astronomer is able to use. Currently, this kind of query requires specific keywords. You can restrict by year range or specify to not or return papers where the author is Max Planck. However, that won't filter out papers that just mention Max Planck in the text. You can also, in specific cases, use outsourced tags from Simbad or NED. Those are manually curated and focus on specific astronomical objects. Our hope is that AstroBERT, being tailored for astrophysics, can help with these kinds of queries automatically or semi-automatically, and do so better than generic language models. Our effort to build AstroBERT has two main motivators, and first one is the now famous BERT paper from Google in 2018. So BERT is a transformer neural network model with attention, and it's modeling English from the Wikipedia in the Brown corpus. That core model was then used to achieve state-of-the-art performances on 11 downstream tasks, and some of those are sentiment analysis, semantic role labeling, word disambiguation. But while the BERT paper goes into technical details of the problems they solve for sequence-to-sequence modeling, from a high-level point of view, what we care about is that they showed that the transformer model can be used as a core for many downstream natural language tasks. Our second motivator is SciBERT by Allen AI in 2019. They took the BERT approach and adapted it to model English from scientific papers taken from the Semantic Scholar corpus. They showed that this adapted model outperforms the original BERT on various scientific domain tasks. This is part of a larger trend that adapts generically successful models to specific language domains. You could say it transfers knowledge from one domain to another sometimes. What we take away from SciBERT is that it showed that BERT can be tailored to specifically scientific text, and we want to tailor it even more specifically to astrophysics. So that's our motivation for AstroBERT. For the remainder of this talk, I will be providing technical detail on how we leveraged our database of scientific papers to design tasks to train AstroBERT, showing the results from the experiments we've run so far and highlighting where AstroBERT outperforms the other models, and finally concluding with our plans for the future, that is, how we will be integrating AstroBERT within ADS and how we will be providing the astrophysics community with access to AstroBERT. I'll now dive into the technical details of our work, and the first step in training any model, neural network or other, is data preparation. This step usually ends up taking longer than we'd like to admit, but without any clean data, we can't train anything. In our case, we have over 15 million records in ADS, but they're not all appropriate for training a model. Some are old and we don't have the content, only the title and the authors. Some were digitized using optical character recognition from scans, which always contains errors. And some contain leftover XML tags and even unprintable Unicode characters. So after cleaning and filtering, we are left with over 300,000 recent astronomy papers containing close to 3 billion words. After filtering and cleaning, we still need to transform the text into a representation that is appropriate for the model, and that's the role of the tokenizer. BERT and SciBERT provide their own tokenizers, of course, but we wanted our own with a vocabulary more tailored towards astronomy. We used our data to train a WordPiece tokenizer. This is the same technology as BERT and SciBERT, and set its vocabulary size to 30,000, also very similar as BERT and SciBERT. Here we have a simple example of what the tokenizer does. It transforms a text string into a list of integers. It starts by adding end and beginning markers, and common substrings are transformed into a single token, while rarer substrings are transformed into multiple tokens, usually in a kind of a stem plus affixes manner. Our AstroBERT tokenizer ends up having 25% overlap with BERT's vocabulary and 35% overlap with SciBERT's vocabulary over the total number of tokens. This is expected, considering SciBERT is modeling scientific papers and BERT is modeling Wikipedia English. And at the end, our final dataset size is close to 4 billion tokens, a size very close to the size used to train the original BERT. With our data prepared, we can now design tasks to train our model. And our first two tasks, which are designed to leverage the fact that we have lots of unlabeled data, are the standard masked language task and the next sentence prediction task. So training a model on the masked language task means feeding the model sentences from our data, tokenized, in which we've masked a random sample of those tokens, and we are asking the model to predict what tokens fit those masks. Doing this, our data takes about 8 hours over each epoch. I've put an example on screen. I'll let you fill in the blanks. In the next sentence prediction task, we are, in addition to doing the masked language task, it's done jointly with the MLM task, we are feeding the model 2 sentences, and we are asking it, are these 2 sentences consecutive in the data? And I've added an example here. I'll let you figure it out if you think it's consecutive or not to the first sentence. Training on the joint MLM plus NSP task takes much longer, as you can see, about 22 hours per epoch, and that's something we're looking into improving. Training models on joint tasks is usually seen as a way to make models more general and useful for downstream tasks, and the first of our downstream tasks is named entity recognition. We extracted about 900 organization names from 44,000 acknowledgement sections. And here is an example of a labeled sentence. Because NER was trained on a smaller data set, each epoch is much faster, 90 seconds per epoch, and we evaluated using tenfold validation for the NER task. I want to emphasize that all three of these models were built on top of each other. So first we trained a MLM model, then we trained a NSP plus MLM model, and both of those models were then used to train separate named entity recognition models. Just so you can make sense of the training times reported, here's the hardware we used and other technologies. So the models were trained on a single machine with two V100 GPUs with 32 gigabytes of RAM each. The machine had 48 core CPU and lots of RAM. And so this is a strong, dedicated machine we purchased specifically for this kind of work. But it's not a full warehouse of servers. And from the software side of things, most of the heavy lifting was done by the Hugging Face Python library, which provides free and open access to the base models and to the datasets we use to compare the results. Some of the other technologies worth mentioning are NLTK for sentence separation, NumPy, of course, and JupyterLab for coding and interfacing with the computer remotely. And here are the first results. This table shows the perplexity scores of our models on our ADS dataset, as well as on various standard English datasets provided by Hugging Face. Because BERT, SciBERT, and AstroBERT all use different vocabularies, scores should be compared across datasets vertically and not across models, except for the two AstroBERT models. Those do use the same vocabulary. What these scores show is that BERT, which was trained on Wikipedia, can be retrained into AstroBERT to perform best on ADS. That is to say, we have a model who has an advantage to be working on ADS as opposed to other datasets. And SciBERT performs similarly on all scientific datasets. As expected, adding another task to the joint training, which is what we do for AstroBERT NSP plus MLM, causes it to do worse in terms of raw perplexity score. That's because perplexity here is just measured in terms of the score on the MLM task. However, when we look at the scores on the named entity recognition task, AstroBERT NSP plus MLM slightly outperforms AstroBERT MLM alone. This is the F1 score across 10 cross-validation runs. And encouragingly, both of these models outperform the original BERT model. With these encouraging results, we can now move forward on our AstroBERT work. So here is a high-level view of the work we plan on doing. First, we're going to need a larger NER dataset. And for this, we've actually already hired a person to hand label more text. We'll continue exploring the best set of hyperparameters to train AstroBERT, and we also want to train variants of AstroBERT, such as a big model and a small model. Once we have a mature enough model, we plan on integrating AstroBERT into our services and providing the community with access to AstroBERT through the Hugging Face Model Hub. And that is the end of my presentation. Thanks everyone for listening.
Thanks very much, Felix. I think we've got time for one quick question, which is in the in Discord. Thomas says, great work. There are plenty of works of the type. How much Sunbird knows in the zero shoot setting about real world? The question is, have you already tried to check how much AstroBERT knows about astronomy?
Yes, thanks for the question. So as you saw in the last results slide, you can take the base BERT model and it gets pretty good results on the NER task, 85% of accuracy, well, 85 F1 score, it's not exactly a percentage, on the NER task. So the question is how much are we improving by training our own? A substantial amount in my opinion, but it's definitely the base BERT model does know something about the English used in astronomy, which Makes sense. It's also English. It's not a foreign language.
Great, thank you very much. I think there might be some more questions coming through, but we'll defer those to the channel. Let's thank Felix again. Right, so our final talk for this evening will be Eric Tollerud talking about a science-centric open approach to Scrum. Eric, all yours.
Yes, just getting the video queued up here.
Hello, everyone. I'm past Eric Tollerud.
And I'm future Eric.
And I want to talk to you today about a software development process we developed at the Space Telescope Science Institute. If process, as opposed to the software itself, is intensely boring to you, feel free to take a power nap right now. But if you're interested enough to ask questions, go ahead and ask straight in the Discord as soon as you think of those questions. Future me will do the best to answer while past me talks. So with that out of the way, let's jump into it. All right, so to understand most of what I'm talking about here, you'll need to know at least a little bit about the team that I'm talking about here. So the work this team has been doing was highlighted yesterday in Ricky Osteen's focus demo. It's the team that implemented the JDA-Viz tools. So this team focuses both on these visualization tools and on broader data analysis tools for JDA-Viz-T, but mainly spectroscopy. So in this context, data analysis is mostly meant to mean sort of after the pipeline, which is really better understood as the part that the scientist has to pay attention to, right? The scientist can ignore the pipeline, but the data analysis tools are the part where a scientist really has to be in the loop, has to sort of have some sort of scientific context thrown in to make the data mean anything at all. This means the tools that this team develops have to be understandable and useful to scientists for their day-to-day work. But most of the developers are non-scientists, right? So that sort of creates a conundrum that this process I'm going to talk about was developed to solve. So the team, before we developed this process I'm talking about, had adopted the methodology called Scrum. So I'm going to take a minute to talk about Scrum, even though it's a fairly standard methodology, because I'm sure many of you are not as familiar with this as those of us who live and breathe it as part of our work. So this team has been following Scrum for the last several years, and Scrum is an agile framework with lots of sort of, suggestions or, if you like, marketable things that trainers can use to sell it to you. But it has a few particular defining rules that really make it Scrum. One of which is time box sprints, where the specific time isn't necessarily set, but for this team was about 2 weeks. And really relevant for this discussion, clearly defined roles. For example, the three primary roles we're talking about here are the development team, the product owner, and the Scrum Master. So to start with, the development team are basically the people who actually do the work, right? The actual software developers. Mostly they're engineers or some form of full-time programmers, but basically what they do is develop the code, sort of own the actual work itself, and even though they pull what they're getting from the backlog, which as I'll describe in a minute, is defined by the product owner. They're still the owners of the actual software development work, right? They have to actually write the code and sort of, in many cases, strategize around the overall architecture. The second role shown here is the Scrum Master. So Scrum Master is often thought of as a servant leader whose job is essentially to organize the process, facilitate and improving it, and sort of help everyone communicate, and in many cases sort of improve the process over time so that the whole team can function effectively. In many cases, they have some other role. In our case, the Scrum Master was typically also a developer, but that's not necessarily a mandatory part of Scrum. What instead I'm going to focus on today is the product owner role. So the product owner role is the person who grooms the backlog, right? That backlog is that thing I was talking about before that the developers draw from when they need to know what work they're planning to do. And it's the product owner who sort of sets the order in which the backlog appears, and effectively that means sets the priority of the work, and does that by acting as the point of contact for stakeholders, right? People who care about the development work. In many cases for our team, this is a mix of sort of scientists and people from NASA or NASA missions or something, or like the mission groups at the Institute and the like. Now note this, these product owners are not the managers, right? They're not the people who actually formally manage the team. In some cases they might be, but in general that's supposed to be frowned upon in Scrum. The product owners in principle are people who are sort of part of the team, considered part of the team, and aren't like formally managed, or formally managers. So you might notice something quite missing here, which is the scientists, right? There's no scientists that appear here. They're the aptly named are not appearing in this film. Now they might be stakeholders, but you know, in principle, in this role, you know, in this sort of formal way of thinking about Scrum, they don't really have any real role. They're far from the code somehow. So what does this mean? Well, they have to fit in somehow, right? For a team that has to worry about science and how the scientists sort of see the code, the scientists have to be involved in some part of the process. So when this team first started adopting Scrum, the initial thought was, well, the scientist or a scientist will be the PO. And that should be easy, right? That seems very straightforward. But this turned out to be bad, right? And this was me, by the way, right? I was tasked to be the PO for this team. And there's many reasons why this is the case. So the first and sort of the clearest one to me is that unlike something like, you know, Microsoft Office, right, a very well-defined application, or at least somewhat well-defined application, where you can state these are the features we want in this team's work, the scientists really care a lot about the details of the code, right? The code and the API and sort of how they work with the code. They don't just care that the spreadsheet appears. They care that this is the name of the function and that it makes sense to them how you call that function, which is quite different from many of the software development teams, where it's really just sort of the features and the end result that matters to people. So that might seem at odds with Agile in some ways, because the whole point is that the team, right, the development team really owns the work. Right, even if the product owners set the priorities, it's really the team that owns the result of the work. So that seems immediately odd that might happen. On top of that, this was just too much, right? There's because of this fact that the scientists care about the details, I had to be much more involved in the sort of day-to-day implementation and make very active suggestions. And given that this was only part of my role at the Institute, there was just not enough time to do an effective job. So of course I had to take shortcuts, and that means this was not an effective PO-ship role. On top of that, it ended up getting really, especially because of these shortcuts, ended up getting dominated by the scientific opinions of somebody who works in near-field cosmology and dwarf galaxy spectroscopy. And since the whole point of these tools is generality, it seemed very bad that it was being dominated by a particular scientist's point of view. And on top of that, even when I could engage scientists, they really had no vested interest in this project because they were, usually just people asked their opinion once in a while. So they would really only do work out of the goodness of their hearts, or when sort of made to do so by a manager or something like that. And that really isn't a recipe for people doing their best work, being sort of forced into it. So instead, we came up with a slightly altered version of Scrum that depends on the concept of what we're calling a PO team. So in many corners of Scrum, this is sort of anathema. This is a thing you're not supposed to do, but we like to think of it as Agile, with a lowercase a. And the way we did this was essentially recruited a group of scientists from sort of various corners of the instrument teams for the James Webb Space Telescope to intentionally span sort of a range of technical or instrument knowledge and skills and interest in the science realm. Now, this team then acted as the product owners, but it's important to realize that this didn't mean like in a given sprint, everybody, there were like 4 people in charge. There was still always a lead PO, because one of the whole points of Scrum is that there's somebody to ask for prioritization. So there's always one person who is the PO for that sprint, but the lead rotated through the several different people. So in practice, as I said before, because a lot of this work is very specifically, tied to sort of day-to-day work that scientists might want to do with their data analysis tools, it means that these POs, because they had the bandwidth to do so, were a lot more engaged in the day-to-day work than is traditional for the Scrum methodology. So for example, I'm showing you here a GitHub issue that was created by a PO, right here, who said, this is the issue we need to solve. And then the same PO was actually reviewing the pull request, right, looking at the code, and even approved the pull request in the end, even though a member of the development team did some of the more mechanical elements of this. So the key idea here is that the POs are really much more actively involved in the process than they would be traditionally, where they just sort of set features and expectations. All right, so what does this get us? So some of the main things that this gets us that are worth highlighting here are that it leads to both a lot better trust between the scientists and the engineers, and it creates a sort of an easier sense of openness. So the way this works is sort of with a PO team like we're describing here. There are multiple scientists who begin to feel like they're sort of a part of the team. They own the project along with the developers. It isn't like the engineers are doing this one project and the scientists are doing a completely different set of projects. So that means they then feel a desire to sort of advertise this work or get their collaborators and their friends in the science community to sort of either give them ideas on how to improve it, or in some cases just say, hey, did you know about this neat new tool we've been developing? And they're much more likely to do that because they're not just like random consultants once in a while. They're actually like genuine members of the team, and they feel like it's part of their almost identity as a scientist now. On top of that, now, unlike the way the team was structured before, the developers and the scientists are now sort of collaborating almost on a daily basis, or at least the lead PO and the developers are. So both start to sort of see each other's point of view, and even learn something, about the day-to-day of the other group. And there's all without the sort of a need for scientists who have qualified engineering knowledge, or that are sort of well trained in the technical skills. It just sort of happens as a part of this more organized Scrum process. On top of that, this is one of the things that sort of leads to this openness, is that the process requires very clear instructions about how you share information between the POs and the development team, which in practice has enabled much better open source practices, because there's these two sort of somewhat different groups, and the POs can almost act like external users of the software, and it becomes part of the process to eat your own dog food, as the saying goes. It becomes sort of more normal to do that. And on top of that, again, because we can have more people by having a team, there's a much better diversity of perspectives in both the code and, of course, the documentation of the code, which is just as important in many ways, because there are several scientists in several different science communities represented, not just that of the PO, essentially. Now, of course, it's not perfect. There are some downsides to this. The biggest one of those that I see is that the POs have to do a lot of syncing up, right? It's very important that the POs view themselves as one unified group, and that just takes extra time. To be fair, when I was doing it by myself, I was probably spending a fair amount of time talking to myself about how to sync up better with what the team was doing, but that's probably my problem, not really Scrum's problem. On top of that, the team has to adopt to different PO styles. That's another downside here, is that each sprint they get a different PO who, even if they try their best, is still not the same person, so there's a little bit more shifting around of style relative to Scrum without a PO team. And on top of that, again, because of this involvement in the day-to-day work, the POs or the scientists have to learn a lot more technical skills than they might be used to. And then, like they might have to learn more GitHub than they would want to, learn about Jira, and maybe like the continuous integration to be able to properly review work. And finally, this communication of the sort of priorities and the backlog need to be shared between the team and the POs, and this can be a little bit problematic because it's another sort of written down line of communication that can leak out into the open space that where we're trying to get input from the external community. That one is probably worth highlighting just a few moments about, which is to say how we do this, right? How we keep that from becoming too big of a problem. The key idea is that we focus primarily on using Jira for setting the backlog, right? So like in this case, we've said one of the priorities of this team for the sprint is to do a particular AstroPi issue, but then all of the content, the AstroPi issue discussed here, and then the sort of initial proposed solution to this issue is written in GitHub, not in Jira, right? So that the general community can actually see that without having to without having to sort of know that we're doing the Scrum process or know that we're using Jira, and they can only see they only need to see the actual code development. But we can add this process on top to make sure that the software is being developed in a way that's productive for everyone. All right. So that's what I wanted to share. So I'll just leave you with a few quick final thoughts. That Scrum can work for open source astronomy software, but only if you put some care and thought into it. In particular, I think we've found that this idea of a team of product owners instead of an individual product owner seems to fit a lot better with sort of astro or science-centric software, especially of the open variety. But I want to leave you with a few tips that might be relevant for you. Right, one of the most critical of this is make sure the product owners sync up regularly and provide a single sort of unified priority and vision. On top of that, make sure everyone is open to rethinking their approach, right? To actually treating the retrospective, which is a traditional part of the Scrum process. Make sure they're actually like genuinely open to this idea, because it's really critical when you have even a larger group of people involved that they'd be willing to adapt their process to current circumstances. And then finally, bear in mind that this idea that I said at the beginning of the talk of science-centric approach to Scrum does not necessarily mean it's scientist-centric. The whole point of this process is that it really made everyone feel an equal part of the team, the POs and the engineers. Even when there's say a scientist telling an engineer what to do or vice versa, there's still an understanding that they're in a team working together. So then the last thing I want to add is a question for everyone to discuss in Discord. Do you feel like this sort of approach could work well in your team or institution? I'm really interested to hear what this group thinks. So thanks for your attention.
Thanks very much, Eric. I see you've been very agile in not listening to your own talk and tackling many of the questions in Discord. I see there are a bunch of people typing, but you have tackled a large number of questions already. Since it is 10 o'clock and people have arrived for the conference photo in Gathertown, perhaps we can tackle the rest of those questions in the dedicated channel. Oleg, is that all right? Is that fine? Sorry. Okay, well, Eric, thanks very much, and yeah, bunch of questions coming through here, but we'll defer that given that it's on the hour and we have the conference photo, the virtual conference photo happening right now. Thank you very much, and another round of applause to all the speakers this session. So 2 quick announcements. One is just that conference photo that's happening in Gathertown now. So those that are online, please congregate for that. And then the second is just a reminder that tomorrow morning we only start at 8:15 South African Standard Time, 15 minutes later than normal at least. But otherwise, thank you very much and have a good evening here in South Africa and a good day around the world.